Hello and welcome back. Let us move on to question number 34. This is a 1-mark numerical answer type question from solid state physics. It deals with lattice vibrations, specifically applying the Debye model to a one-dimensional system. We need to calculate the velocity of sound given the phonon density of states. The problem states, consider a monoatomic chain of 30 centimeter. The phonon density of states is 1.2 times 10 to the power minus 4 seconds. Assuming the Debye model, we need to find the velocity of sound in meters per second rounded to one decimal place. First, let's catch the units. Length is in centimeters, so we must convert that to meters, which is 0.3 meters. The density of states is given in seconds, which implies dn over d omega. Alright, so to solve this, we need the expression for the density of states in one dimension. Recall that for a one-dimensional chain of length L, the density of modes in K space is L over 2 pi. In the Debye approximation, we assume a linear dispersion relation, that is omega is k times Vs. This means dk is simply d omega over Vs. Okay, and since phonons can propagate in both forward and backward directions, that is positive and negative k, we multiply by a factor of 2, accounting for plus or minus k. So we have g of omega. So if we simplify this, we get the standard formula for 1D constant degrees of states, that is g of omega dn over d omega is simply fraction of L and pi Vs. So if you just simplify this, you will get this. Note that in one dimension, the density of states is independent of frequency, so it's a constant value. So this is a point to be noted. Now let us rearrange the formula to solve for Vs. So if you just rearrange that particular formula I wrote in the last slide, so we get the formula for Vs, so which is nothing but L over pi times g of omega. Now if you substitute the values, that is L, which is 0.3 meters, pi is approximately 3.14, and g of omega, which was given as 1.2 times 10 to the power minus 4, if you just execute this, we get 0.3 divided by 3.14 times 1.2 times 10 to the power minus 4. So if you just simplify this, you will get it around 795.77. So if you round it to one decimal place, our final answer is nothing but 795.8 meter per second. Alright, so before we finish, here is a quick takeaway for this particular problem. So this question relied on one dimension density of states. So it is crucial to remember how the density of states, that is g of omega, depends on frequency for different dimensions in the Debye model. So in one dimension, it is a constant, as we just saw. In two dimensions, it is a linear in omega, and it is quadratic, that is omega squared, in 3 dimensions. So remembering this trend can help you quickly solve proportional reasoning questions for the Debye model. So for a deeper understanding of lattice dynamics and the derivation of density of states in different dimensions, check out the condensed matter physics course by Professor Harbola from IIT Kanpur. The lectures on heat capacity cover the Debye model extensively. That's it for the solution of question number 34. See you in the next one.